Welcome to M. Wisely's Cafe. Ejner Fulsing was an Army helicopter pilot in Korea from 1969 to 70, later attending West Point, where he graduated in 1974 with a B.S. in engineering. After leaving the Army in 1979, Ejner spent the next 20 years working in engineering and marketing. He spent the last 10 years before retiring as a proposal manager at NASA Ames and SETI, helping scientists write proposals for space missions. He is most proud of his contributions to the Icebreaker mission, which was designed to search for microbial remnants of life on Mars. 20 years ago, Ejner took up writing. He writes in the hard sci-fi genre, where all science and technology must be plausible. The Galactican series depicts the scientific, technological, and societal evolutions that a society will have to make in order to become a true spacefaring society.
I'm retired from NASA. I spent about 10 years at NASA Ames Research Center over at Moffett Field, and my primary function there was helping scientists write proposals for space missions. Got to write, typically I specialized in the science part. And I got to talk to and get yelled at and sworn out and have my parents' marital status questioned by some of the finest intellectual minds in the nation. Anyway, after retiring from NASA, I've devoted most of my retirement time to working on a series called the Galactican series. It's going to be a 6 books when it's completed. I've got 4 up on Amazon right now, and the idea is that it will trace mankind's technological, biological, sociological evolution toward becoming a spacefaring society. And today's talk is basically why we need to become a spacefaring society. So with no further ado, shall I sally forth with my speech? I'll take that as a yes. Okay. Basically, in 1950, Enrico Fermi asked a question: where are they? His now famous paradox referred to alien visitations, perhaps inspired by the Roswell incident of 1947. With possibly 400, yes?
Were you supposed to be sharing your screen now? We're not seeing it.
Oh, where did it go? Okay, how do we get the screen back?
So you go down to share screen, share.
Share screen, got that.
And then pick your PowerPoint, just like you did before. I knocked you off so I could share.
I see.
My screen.
Okay, how about, here we go. That one. And I'll hit share.
And it's coming up. You're good.
Okay, so let's see, where was I here? Okay, since then, the notion of alien visitations has proven irresistible to conspiracy theorists, offering a variety of explanations roughly divided among intricate physics explanations, government cover-ups, and anthropomorphized interpretations of alien intent. Personally, I think the real answer is patently obvious based on 2 premises. The first is that Earth and all other habitable planets in the universe have use-by dates. The second premise I'm saving for the end of the talk, so please don't change the channel. It's actually pretty cool. Meanwhile, Earth formed 4.6 billion years ago and has been living on borrowed time ever since. If humans don't destroy it first, our sun will surely destroy it for us. For the sake of my first premise, I'm going to discuss 4 different artificial failure modes and 5 natural ones. It's a plausible assumption that all the other habitable planets in the universe, especially the ones that host technically savvy civilizations, will suffer the same or similar fate. So we can shed a lot of light on Enrico's paradox by using Earth as an analog. Okay, as I said, I see 4 candidate artificial failure modes. There's probably more, humans being the devious little bastards that they are, but don't take my word for it. This guy is a theoretical physicist, but what do they know? Okay, for years, Hollywood writers have tried to convince us that AI will somehow become sentient, go rogue, and then decide to wipe out humanity. Here are some examples to refresh your memory. HAL 9000 begins to malfunction, so killing off the crew became necessary for mission success. The Matrix thinks humans are only good as batteries, plus Agent Smith thinks we stink. Skynet thinks we're going to turn it off, so preemptively it tries to turn off the humans. Westworld robots got tired of always having to lose gunfights, plus various other abuse, so they decided to kill off the staff. All of the above presume that AI sentients care whether we live or die. Spoiler, they don't. For that matter, they don't care whether they live or die. So why does Hollywood keep perpetuating such myths? Put simply, sells tickets. Now, I confess that I've seen and taken guilty pleasure in every one of the movies listed above. And as a novelist, I can understand the need for villains. The AI gone rogue theme is an easy mark, even if it ain't necessarily so. So why do I call out AI as a failure mode? Not because it turns against us, but because it works exactly as intended. AI will enable wealthy oligarchs to make the rest of humanity irrelevant. Stop and think like an oligarch for a minute. Humans are lousy employees. They're expensive, unreliable, and worst of all, whiny. On the other hand, robots are wonderful employees. They're cheap, they're reliable, and they have the good taste never to complain. The goal of these oligarchs is to eliminate as many whiny humans as possible from the workforce. Society under this model will eventually be divided into 3 groups. The ones who own the AI robotic factories, namely the oligarchs, the privileged few who can still find jobs in those factories, and the homeless. Now, some of you may be wondering, if all the factories are staffed by robots, there will no longer be any paychecks to bring home, so who's going to purchase all the goods from those factories? It's not a popular breakout topic at Davos. Wealthy oligarchs generally don't think about it, and the few that do regard it as a problem for some other oligarch to worry about. AI-enabled oligarchy represents a very high severity risk, with the probability of occurring this century on the order of 40 to 65%. Climate-driven civilizational destabilization looks like it's manageable until it's not. It's akin to the frog placed in a pot of water and slowly brought to a boil. By the time he realizes the water's hot, he's dead. This problem attacks nearly every foundational system upon which modern civilization depends. Food production, water availability, energy generation, public health, and political stability. One of the most severe is sea level rise caused by the complete melting of the Greenland and Antarctic ice caps. Ultimately, sometime in the next 10,000 years or so, a full melt of both ice caps will raise global sea levels by some 70 meters. Think about that the next time you list your house. But things could happen in the interim on a much tighter schedule. I'm referring to the collapse of the Antarctic Thwaites Glacier and the subsequent collapse of the Western Antarctic ice sheet. This is the Thwaites Glacier right in this area, and next to him is his neighbor, the Pine Island Glacier, and the two of them together act like kind of a cork that's holding the entire Western Antarctic ice sheet in place. Basically, what we have in the way of a schedule is right now we're looking at sea level rise of approximately 0 meters. And if the Thwaites destabilizes sometime in the next 25, maybe up to 2150, we're looking at another half to a meter of sea level rise. And then the subsequent Western Antarctic ice sheet cascade will begin. That'll take place from, say, 2100 to about the year 3000. And that'll give us up to maybe 5 meters. That's about 15 feet of sea level rise. Long-term ice sheet loss altogether, that's the full Greenland and East Antarctica if warming persists, that's up to 70 meters. You can go to the NOAA Sea Level Rise Viewer. I have here Palm Beach, Florida at the present time. And if you look really closely, that spot right there in the middle, that's a little place called Mar-a-Lago. This is Mar-a-Lago with 10 feet of sea level rise. Climate-driven civilizational destabilization represents a high severity risk with a probability this century on the order of 20 to 40%. Next up, engineered pandemics can attack not just humans, but agriculture and livestock. Unlike natural pandemics, engineered pandemics are optimized for virulence and transmissibility. As soon as a natural pandemic takes root in its host, it begins evolving toward lessened virulence, it not being in its best interest to kill off its host. Weaponized pathogens scare the hell out of governments. As soon as a bioweapon is released on a target nation, a race begins to contain the outbreak before it overwhelms the population. First, the target nation has to detect the pathogen and realize it's under attack. Then it has to isolate a population that may or may not cooperate with quarantine measures. Meanwhile, scientists are racing to develop a countermeasure, most likely some form of mRNA vaccine because they can be developed quickly. Then comes mass production and nationwide distribution, while hospitals are already overflowing with casualties. All of this is happening while the government is still trying to identify the source of the attack. Because if it was deliberate, there will be enormous pressure to retaliate. Engineered pandemics are an ideal weapon of mass destruction in that the attacking nation can first vaccinate its own population, thereby only affecting the target population and anybody else who happens to be downwind. By the time the attacking nation is identified, if at all, the damage is done. They can be developed in relative secrecy without attracting the same level of scrutiny as, say, nuclear weapons programs. Look at Iran's experience pursuing nuclear capability. The regime faced decades of sanctions, covert operations, and ultimately direct military pressure. Other hostile governments will study the outcome carefully, and the lesson that they may draw is that overt nuclear programs invite overwhelming external attention, while biological deterrents are far harder to detect before deployment. Containment presents another problem. Weaponized pathogens do not recognize national borders. What takes root in one target nation can quickly spread into neighboring states and eventually throughout the global transportation network. A sufficiently ruthless aggressor, particularly one that has quietly vaccinated its own population beforehand, could potentially hold much of the world hostage while remaining comparatively insulated from the outbreak itself. Finally, desperate targeted nations may resort to indiscriminate responses, nuclear weapons launched at whomever, thereby exacerbating the threat to world order. Engineered pandemics represent a high to extreme severity risk with a probability this century on the order of 10 to maybe 25%. Oops, I got ahead of myself there. There we go. Okay, nuclear weapons are spreading in spite of the Nuclear Non-Proliferation Treaty. Since World War II, we've gone from one nuclear nation to 9. from 2 warheads in 1945 to over 12,000 today. Roughly 85 to 90% of them still held by the United States and Russia. U.S. efforts to topple unsavory regimes have had the predictable side effect. They incentivize other nations to pursue nuclear capability as life insurance. North Korea already possesses dozens of warheads and continues to expand its stockpile. Iran does not currently have nuclear weapons, but the broader dynamic is clear. States that feel exposed seek deterrence. We also understand something else. A local nuclear exchange does not stay local for long. Escalation pathways exist, and once activated, they're extremely difficult to control. World War II showed that large-scale wars can be initiated by highly centralized leadership, making aggressive decisions under perceived threat, paranoia. Extending a conventional conflict into a nuclear one would depend on the same mechanism. Decisions made under pressure with incomplete information and very little time. During the Cold War, the United States and the Soviet Union developed a doctrine, a mutually assured destruction, or MAD doctrine. That imposed a kind of grim decision-making. The Cuban Missile Crisis of October 1962 is the classic example. I was in the 8th grade, and I remember gathering in my school's hallway for duck and cover exercises. A very good friend of mine, Chet Nagel, who is about 10 years older than I am, flew S-2 trackers off the USS Randolph. Randolph at the time was rigged for anti-submarine warfare, which is why you see so many trackers on its deck instead of fighters. On October 27th, while I was busy ducking and covering in the hallway, Chet's ship and 11 destroyers entrapped a Soviet Foxtrot-class submarine. That was a tense moment, since the Soviet sub-captain was ready to fight his way out with nuclear torpedoes. Fortunately, he opted to surface and wait for instructions from Moscow. The next day, October 28th, leaders on both sides stepped back from the brink. Both Washington and Moscow made concessions behind the scenes, allowing each side to de-escalate without further humiliation. Sanity was restored. Chet landed his tracker in time for happy hour, and I went back to algebra. Today, deterrence still exists, but the system it operates within has changed. There are more nuclear-armed states, more diverse doctrines, and more independent decision centers. The number of nuclear decision points has increased, and the consistency of judgment under stress cannot be assumed. A historical example illustrates the margin. In the early days of the Yom Kippur War of 1973, Israel faced an existential crisis as Egypt attacked across the Suez Canal, while Syria attacked across the Golan Heights. Israel's senior military leader, Moshe Dayan, took prudent steps to ensure that all strategic options, including the nuclear deterrent, could be readied if the situation deteriorated further. Israel's political leadership under Prime Minister Golda Meir then had to weigh those options against their consequences. Meir ultimately chose restraint. The use of nuclear weapons might have actually been militarily decisive, but it would have crossed a threshold with incalculable political and strategic costs. That decision mattered enormously. I leave it to your imagination to replay the Yom Kippur situation with today's leadership. Nuclear war represents a medium to extreme severity risk with a probability of occurrence this century on the order of 5 to 15%. Here's a summary table of the artificial failure modes. Note, they focus on destroying civilizations, not the planet. Note also that while we can experience multiple artificial failure modes at once, we only need one. Natural failure modes. Before we get deep into natural failure modes, I want to be clear about something. They don't have the urgency of artificial failure modes. Natural fails unfold over tens or sometimes hundreds of millions of years. They're not the decadal or century scale of artificial failures. Hence, they're understandably harder to get worked up about. You don't need to quit your job and try to squeeze in one last trip to Disneyland. Natural fails establish a boundary condition. They tell us that even if we navigate every artificial risk perfectly, even if we get our act together as a civilized species, the planet still has a finite shelf life. And that matters because it means survival is not just about avoiding failure. It's about eventually leaving. In other words, the natural risks don't create urgency. They remove the illusion that staying here indefinitely is an option. Now let's drill down into some of those natural failure modes. As with the AI threat, Hollywood has done us no favors here. According to the movies, asteroid defense consists of discovering the problem at the last possible moment and solving it with a nuclear bomb emplaced by a crew of misfit astronauts. It makes for great cinema. It's a Hail Mary, and everybody lives a good Hail Mary story. But with all due respect to Bruce Willis and Andy Weir, Hail Marys only work in Ronald Reagan movies. A more realistic approach involves early detection and a tiny nudge. Of course, that movie would flop at the box office. The real story starts by separating two things that we tend to lump together, asteroids and comets. They're different problems. The dangerous asteroids are not sitting quietly in the main belt or out among the Jupiter Trojans. Basically, we're showing three different kinds of asteroid here. This big belt right here in the middle, the big white one, is the asteroid main belt. And then Jupiter has three groups of asteroids collectively known as the Trojans. So we got, they tend to hang out at the L4 and L5 Lagrange points. And then you've got the Hildas out here. They always show them at the L3 point, but realistically, they orbit the sun on a kind of a 3-2 resonance with Jupiter. Excuse me. There are about 1 million asteroids in the main belt, and Jupiter is tended by about 15,000 Trojans and maybe 7,000 Hildas. Those asteroids tend to stay in their lanes. The dangerous asteroids are what we call near-Earth asteroids. That's those ones inside the orbit of Mars here, the little green ones that you see. Okay, they're the ones whose orbits cross or approach Earth's orbit. They call them the Amors, the Apollos, the Ejners, and the Ejners. As you can see, the Amors tend to stay outside the orbit of Earth. The Apollos and the Ejners both cross the orbit of Earth, and the Ejners tend to stay completely inside the orbit of Earth. There are quite a lot of them, about 40,000. And of those, over 2,500 are what we call potentially hazardous asteroids, or PHAs. By definition, PHAs come within 0.15 astronomical units of Earth. That's 7.5 million kilometers. And they're 100 meters in diameter or larger. The largest is an asteroid called Tutatis at 5.4 kilometers. There's about 153 PHAs that are larger than a kilometer. The most threatening is Bennu at half a kilometer. It has a 1 in 2,700 chance of striking the Earth on September 24th, 2182. Mark your calendars. Damage effects of PHAs vary by size. At the 50 to 100 meter size range, we call those local or city killers. The ones that go 300 to 500 meters, we call those regional destroyers. 1 kilometer is a global catastrophe. 5 kilometers, civilization threat. And 10 kilometers, we're talking mass extinction event. Examples, we've got a fairly small one, about 60 meters. And it would likely be an airburst or maybe a city scale of destruction. Historically, Tunguska, or if you want, you can go just outside of Winslow, Arizona and see the Barringer crater. It's almost a mile across and it's pretty deep. let's see, Chicxulub, the one down here at the bottom, happened about 66 million years ago, and it destroyed the dinosaurs. Okay, I've got the known PHA example here for that one is Eros. It's 17 kilometers in diameter, quite a bit larger than Chicxulub. It's not technically a PHA because its minimum orbital intercept distance is 0.15 astronomical units, and the formal PHA threshold is less than or equal to 0.05 astronomical units. Again, 0.05 AU would be about 7.5 million kilometers. Near-Earth asteroids tend to be slower than comets, typically on the order of 12 to 25 kilometers per second. This is important for two reasons. Being slower, they do less damage pound for pound, and it also gives us time to decide what to do if one is on a collision course. Apophis is an interesting example. It's an ATEN, which makes it an Earth crosser, which it does with some regularity, about every 8 years or so. It's about 350 meters average diameter, which means if it does hit Earth, it'll be a regional disaster, say Iowa or something about that size. The next near miss is forecast for April 13th, 2029, and the one after that is April 13th, 2036. Again, mark your calendars. In 2029, it will come within 32,000 kilometers of Earth. That's inside the orbits of typical geostationary satellites. And in 2036, it'll pass within 8.4 million kilometers. That's million with an M. Okay, we've spent decades building a detection and cataloging system specifically for near-Earth asteroids. Missions like NEOWISE, which was deorbited in 2024, have surveyed the sky in infrared, helping us find dark objects that visible light telescopes might miss. It's going to be replaced by NEO Surveyor, a purpose-built mission expected to be launched around 2028. This is a picture of NEO Surveyor, and it operates, it'll orbit the Earth at what they call the L1 Lagrange point. That's a huge potato-shaped orbit, about 1.5 million kilometers from the Earth's surface toward the sun. It's got a 50-centimeter infrared telescope, and it'll have enough sensitivity to detect asteroids as small as 10 meters in diameter. This entire architecture is backed by congressional mandate called the Near-Earth Object Observation Program. It requires NASA to find at least 90% of near-Earth objects larger than 140 meters. Of course, somebody needs to remind Congress that an awful lot of damage can be done by an asteroid of only 50 or 100 meters. But for the most part, it works. For large asteroids, warning times can extend to decades or from years to decades. That changes everything, because if you have time, you don't need to blow the object up. You just need to give it a little nudge. Done early enough, a nudge can deflect a large asteroid away from a collision trajectory. We proved that with NASA's DART mission back in 2022. With DART, a spacecraft about the size of a vending machine impacted Dimorphos, a small moon of PHA Didymos. I don't know if I'm pronouncing that right. Probably some Greek god whom I hope I didn't offend. Anyway, it shortened its orbital period by some 33 minutes, equivalent to slowing its orbital velocity by 2.7 millimeters per second. Didymos is an Apollo, an Earth crosser, about 765 meters in diameter, while its moon Dimorphos is about 150 meters. First off, kudos to Johns Hopkins Applied Physics Lab for their target shooting. Second, I want to emphasize that while 2.7 millimeters per second may not sound like much, the idea is to catch these guys way early in their collision trajectory with Earth. 2.7 millimeters per second works out to 43 kilometers over 6 months. That's pretty significant for a proof of principle mission. We've reduced the problem to a matter of numbers. No nukes, no drilling, no heroics. Asteroids are a problem we can work on. Comets are not. They come in three flavors. You've got your long period comets. They come from the Oort cloud and they have a period of over 200 years. You have short period comets that come from the Kuiper belt, and they have a period of typically less than 200 years. Main belt comets hang out in the asteroid belt, and they have variable periods, and they're rare hybrid objects that don't have much of an impact threat. This kind of gives you a visual of what we're talking about here. The long period comets are out here in the Oort cloud, which starts at 2,000 astronomical units and goes to 200,000 astronomical units. Just so you can visualize, 200,000 astronomical units is 3/4 of the way to Proxima Centauri. But that's where the long period guys come from. They get jostled by something passing nearby, a rogue planet or something like that. It sends them shooting into the inner solar system, and next thing you know, everybody is like, oh my God, what are we going to do? And then they pass by, and that's it. We never see them again. Kuiper belt objects, on the other hand, are where these short period comets come from. They're out here in this band just beyond Neptune, from 30 to 50 astronomical units. And then inside Jupiter, but outside of Mars, we have the main belt asteroids, which is where the main belt comets come from. Comets tend to be larger than asteroids, typically on the order of 1 to 10 kilometers across, and they come in a lot faster, often 30 to 70 kilometers per second. That alone means much higher impact energy. For example, a comet coming in 4 times faster than an equivalent mass asteroid doesn't just hit 4 times harder. It hits a full order of magnitude harder. But the real problem is not speed, it's detection. Now, here's an image of the dark sky. And next up, I'm going to show you an image of a distant comet against the dark sky. Out beyond Jupiter, greater than 5 astronomical units, a comet is just a dark spot against a dark sky. It doesn't look like the familiar image of a comet with a bright tail spewing from it. That only happens when it gets close enough for the sun to sublimate its ices and form a coma at about 3 to 5 astronomical units. Inside the orbit, that would be inside the orbit of Jupiter. By then, impact may only be a few months away. Yes, we have detected interstellar comets like Oumuamua and Borisov, and more recently 3I Atlas, but these were incidental discoveries. They were not the result of a system designed to find inbound long-period comets early enough to matter. We do not have a comet defense program comparable to our asteroid defense program. Not because we don't care, but because we have no mitigation technology that could work in that amount of time. The good news is that comets impact on Earth far less frequently than asteroids. Kilometer-scale asteroids strike Earth about every million years. Comparable comets, perhaps every 10 to 20 million. Planetary defense is still necessary, and we should keep detection and tracking telescopes in space. And we should refine our deflection technologies. But in spite of our best efforts, some impact threat is eventually going to get through. Probably a fast-moving, late-detected, long-period comet. Over a long enough period of time, even low-probability events become inevitable. If humanity remains on Earth long enough, something is eventually going to get through, which is why sooner or later, we got to get off this rock. I'm switching up the time frame of the natural failure modes to account for the probability of occurrence by year 3000 rather than by the end of this century. Natural failure modes are much fewer and farther between than artificial failure modes, but they do tend to be a good deal more severe. Asteroid comet impact of global catastrophe scale represents an extreme severity with a probability of occurrence by year 3000 on the order of something under 0.01%. Volcanic disasters come in two flavors, what I euphemistically call boomers and gassers. Boomers, like Krakatoa or Mount St. Helens, are fairly common. They're caused by high viscosity lava that acts like a cork, building up pressure. They're rated on a logarithmic volcanic explosivity index, a VEI, going from 0 to 8, according to the volume of the ejecta. The Yellowstone volcano that went off 600,000 years ago was an 8. Krakatoa, 1883, was a 6, and Mount St. Helens, 1980, was a 5. They're loud and spectacular, but they don't last long. They can have a huge pyroclastic flows that wipe out cities, but they don't wipe out civilizations. They can cause short-term climate change. For example, the year without a summer, Mount Tambora, 1815, that was a VEI of 7. But they don't cause mass extinctions. Right now, there's about 117 active boomers, with 61 having erupted in 2025 alone. Gassers are much rarer and can cause mass extinction events. The most notable was the Siberian traps of 251 million years ago. It lasted 2 million years. It wiped out 81% of marine species and 70% of terrestrial vertebrate species. It took 10 million years to recover. The word traps and Siberian traps refers to the leftover basaltic fields from these eruptions. The lava is extremely low viscosity, allowing it to cover wide regions. They're formed by massive fissure eruptions where magma erupts from long cracks in the Earth's crust. At maximum extent, these Siberian traps covered roughly 5 to 7 million square kilometers. That's about the size of Australia. The damage of gassers compared to boomers is compounded by several factors. First off, long duration gassers last millions of years. And second, Siberia had an overlying hydrocarbon sediment basin, which was superheated by the lava and then ignited by the sudden exposure to atmospheric oxygen. This caused a voluminous release of greenhouse gases, methane and CO2, which outgassed much faster than could be absorbed by Earth's natural carbon sinks. CO2 levels during the Siberian traps may have gotten as high as 8,000 parts per million, compared with today's 433 parts per million. Global average temperature may have gotten as high as 35 degrees centigrade compared to today's 15 degrees centigrade. Even longer, they also are characterized by an even longer recovery period, 10 million years. It's a miracle that the Earth's It's a miracle that the Earth's biosphere survived at all. Trap scale events historically happen every 20 to 30 million years, and while the frequency and severity of massive fissure eruptions has been tapering off due to Earth's cooling, that does not mean that we're done with them. We have 3 potential future traps that we know of. There's the East African Rift, the EAR, predicted to blow in 10 to 50 million years. There's the South Pacific seafloor, predicted for 50-odd million years. And then there's Iceland, which so far has been limited to regional lava flows. You may be wondering about the Yellowstone volcano. It erupts every 600,000 years ago. The last one was about 600,000 years ago. My wife Julie and I are planning to squeeze in one last trip to Yellowstone in September. We're going to keep it brief. While the Yellowstone did a lot of damage, I left it off the list because it's a boomer, not a gasser. Also, compared to the Siberian traps, the East African Rift is not sitting on a carbon bomb. It will only produce about a quarter of the lava volume of the Siberian traps, and its rate of eruption is expected to be slow enough to be absorbed by Earth's natural carbon sinks. Supervolcanic trap-scale eruptions represent very high to extreme severity with probability of occurrence by year 3000, again, under 0.01%. Natural pandemics, where we already discussed engineered pandemics, we'll move on to natural pandemics. Unlike engineered pandemics, natural pandemics are optimized for their own survival. It is not in their best interest to kill off their hosts. Hence, as soon as they infect a host, they begin evolving towards reduced virulence and increased transmissibility. Having said that, natural pandemics can still be quite severe, as the following comparison of the Black Death of 1350, the 1918 influenza, and the 2019 COVID-19 pandemic show. As the body count suggests, we've learned quite a bit since 1350. Most natural pandemics are predictable, giving us precious time to develop a means of combating the pandemic, assuming intergovernmental cooperation. Most natural pandemics have zoonotic origins, meaning they jump from animals to humans. They have predictable points of origin, typically poultry and swine farms in Southeast Asia. This is not anybody's fault. It's a natural phenomenon that's been going on for millennia. But it does suggest maintaining a good relationship with these nations is in our best interest. Failing that, we can wait for patient zero to show up and start working on containment from there. If we're paying attention, assuming government cooperation, we can buy time. Time to identify the pathogen. Time to develop countermeasures. And here's where modern biology has changed the game. mRNA vaccines allowed us to design and deploy a response in months instead of years. That's a genuine breakthrough. The remaining problem is not scientific, it's human. We still have to convince a large fraction of the population to accept vaccinations. Hence, a biological problem has become a social one. There's quite a spread in severity and probability for the three examples I gave. Tough to find a balance between the severity of the disease and the ability of modern medicine to combat it. Solar super flares in extreme space weather are not new. What is new is us. For most of human history, a major solar storm was a curiosity. The sun burped. There were spectacular auroras. People wrote it down in their diaries. And that was the world of 1859. The Carrington event of that year was the largest geomagnetic storm in recorded history. It lit up the skies from the tropics to the poles. Telegraph systems sparked. Operators got shocked, and in a few cases, equipment caught fire. But that was it. There wasn't much else to break. Now, fast forward to today, we've built a civilization that runs on electricity, electronics, long, fragile, interconnected networks, power grids, satellites, GPS, communications, and financial systems. We didn't make ourselves more robust. We made ourselves more dependent. Now, what would happen if we had a repeat of the Carrington event today? First, what is it? The sun occasionally ejects massive clouds of plasma called coronal mass ejections. See if I can get this guy going here. Here we go. Oh, great. It comes with sound effects. Anyway, you can see what's going on here is we've got the sun spewing out. All right, I'm going to quiet him down. It looked really good, but I didn't realize it was going to have sound effects. When one of those CMEs reaches Earth, it doesn't just give us pretty auroras, it distorts the magnetic field, and that in turn induces electrical currents in anything long and conductive, such as power lines, pipelines, undersea cables. In other words, our power grid becomes the antenna. In 1859, the Carrington event mostly disrupted telegraph systems. Today, it would hit something far more fragile, a civilization built on interconnected electrical and electronic infrastructure. Large transformers overload. Sections of the grid collapse. Satellites suffer radiation damage. GPS and communications degrade or fail. And unlike a local blackout, Large power transformers are custom-built systems with replacement times measured in months or years. A major solar storm doesn't kill people directly. It turns off systems that keep them alive. And because modern civilization is tightly interconnected, got power, communications, finance, logistics, food distribution, it's a cascade of failures. What begins as a space weather event can quickly become economic disruption, infrastructure failure, and social instability. The real problem is not the initial damage, it's the recovery time. We know how to build modern infrastructure. We don't know how to rebuild it quickly under degraded conditions. A Carrington-class CME represents a high severity with a probability of occurrence by year 3000 of high. Okay, our final contender here, long-term solar evolution. Most people have a mental model that goes something like this. Civilization is busy chugging along, and then 5 billion years from now, the sun reaches the end of its life, and only then does everything end. Actually, between now and the next 5 billion years, the sun will indeed exhaust its core of hydrogen, and it will become half again as bright, but only about 10% larger. Then at the 5 billion year mark, the sun will leave the main sequence, where its core fusion's outward pressure balances gravity's inward pressure, and enter the red giant phase, where it will increase rapidly in luminosity and size. The last couple of 100 million years, from approximately 5.8 to 6 billion years from now, its diameter will subsume the orbits of Mercury, Venus, and possibly Earth as it becomes a red giant. If the Earth somehow does survive, it will be as a charged cinder with all life sterilized from its surface. Then over the next few billion years, it'll enter the planetary nebula phase, where it will shred off its outer layers, losing half its mass in the process. What will be left is a white dwarf. It'll be half the solar mass, the original solar mass, crammed into a volume the size of Earth. The outer layers will disperse into the interstellar medium. But humanity will never see any of that, not if they attempt to remain on Earth. Long before, starting about 200 million years from now, the sun's luminosity and radius will increase by about 2% and 0.2% respectively. That's enough to cause noticeable warming on the Earth's surface. Between 200 and 500 million years from now, the sun's luminosity and radius will have increased 5% and 0.5% respectively, enough to cause severe stress on ecosystems. By 800 million years, luminosity and radius will have increased 8% and 0.8%, and we will experience runaway greenhouse effects similar to Venus. By a billion years, the oceans will be gone, boiled away, and complex life will have ended. The question is, how severe do things have to get before the Earth becomes untenable to humanity? Here we have a chart showing the somewhat shortened phase from today to 100 million years to 200 million years to 300 million years. The Earth's current average temperature is 15 degrees centigrade. Bear in mind, that's a global average. Global means temperature swings vary between 10 degrees centigrade and 25 centigrade. For you Fahrenheit fans, that's a typical swing from 50 to 77 degrees. It looks fairly benign, and it is. We have a stable hydrological cycle. There's ice caps. Sea level is manageable. Agriculture works, and civilization is optimized. In 100 billion years, average temperatures will go up to 17 degrees centigrade. That's 63 Fahrenheit. Global mean temperature swings vary between 12 centigrade and 27 centigrade. It still looks benign, but not really. We're looking at strong warming, weather variability increasing, crop yields unstable, civilization will exist, but only under stress. By 200 million years from now, we'll be at 20 degrees centigrade. Global mean temperature swings vary between 15 and 30 degrees centigrade. Again, global mean temperature ranges look benign, but at these levels, polar ice is mostly gone. Sea levels will have risen 70 meters. There will be large regions that are intermittently uninhabitable. Civilization will become fragile and uneven. And by 300 million years, we'll be at 24 degrees centigrade. Global mean temperature swings vary between 19°C and 34°C. I know, these sound like temperatures you pay to vacation in, but taken globally, this will not be a summer in Cabo. There will be persistent heat stress in the tropics accompanied by large-scale agricultural collapse. Complex life may exist, but civilization will be on the verge of global breakdown. Geologic eras on Earth typically last a few hundred million years. The Mesozoic era, the age of dinosaurs, that lasted from roughly 252 to 66 million years ago. It was about 200 million years in duration. We're now 66 million years into the Cenozoic era, the age of mammals, and with perhaps another 200 million years before humanity runs out of viable climate. It is possible that we are living in Earth's final great era, kind of our own last of the Mohicans moment. For some reason, I find that thought sobering. Meanwhile, back to the Fermi paradox. As previously stated, Earth formed 4.6 billion years ago. The first microbial life forms formed 500 million years after that. That's roughly 4 billion years spent going from single-celled organisms that barely knew how to eat and reproduce to where we are now, a somewhat tech-savvy species who conquered the boundary of space back in 1961. 65 years later, we're immensely proud of ourselves for sending 4 astronauts slightly past the moon. So, from astronauts traveling slightly past the moon to humanity leaving the solar system and living among the stars, and we need to achieve that within the next 200 million years. Bear in mind that 200 million years is a hard stop, as in game over. Our actual time allotment is probably a lot less given all the failure modes I just outlined for you. Each of the 4 artificial failure modes represented has a significant probability of occurring before the end of the century. Natural disasters are a bit farther apart, but they're potentially a lot more severe. I don't show any risk or probability estimates for long-term solar evolution because it's an absolute. I.e., as I previously apologized to Andy Weir, you cannot fix the sun. What happens if we fail? Not much, really. The universe will go on, just without us. Recall my first premise at the beginning of this talk. In the vastness of the universe, failed star systems are routine. Our extraordinary bipedal, opposable-thumbed, big-brained, tech-savvy, lunar-exploring, one-of-a-kind civilization really doesn't matter. No civilization does. The universe simply doesn't give a damn. It casually snuffs out any civilization that fails to escape its star. And therein lies my second premise. Ever since the first microbe formed on whatever habitable planet it decided to call home, life on that planet has been in a race to evolve beyond its stellar boundary before they, or their planet, or their star, destroys them. Okay, here it comes. The fact that we never see any alien civilizations suggests that most don't make it. Are you listening, Enrico? I told you it was cool. Which leads us to a very simple question. What we're talking about here is not a mission. It's not a permanent colony on the lunar surface or even the Martian surface. Both the moon and Mars will succumb to our end of sun. We have to go beyond the solar system. We have to go out to the stars, to live among them, to use whatever resources we can scrounge along the way to recursively manufacture new starships and new crews to man them. This is not exploration. This is expansion. It's a civilizational transition on a scale that does not happen in a fragmented tribal system such as we have always known on Earth. This will require sustained coordination, shared priorities, and time horizons measured in generations. In short, our civilization must abandon its tribal ways in favor of a singular global society. Now, do you want to know how absurd that notion is? Yeah, I know. It ain't going to happen, Skippy. But if we don't cooperate at that level, we don't get to the stars. And if we don't get to the stars, we don't survive. So let's pretend for a minute that we could somehow learn to cooperate on that scale. What would it look like? We need an industrial mobile civilization operating in deep space. The architecture would look something like this, as depicted on the cover of Book 6, Ross 128b. I'm hoping to get that up on Amazon in a couple of years. The fellow up here on top is a guy that I knew briefly just before he died in 2022. And down here on the left is Pete Worden, my old boss at Ames. Then we have Dr. Jill Tarter. You probably heard. She's the basis for the character Jodie Foster played in Contact. And then here's a SETI scientist, Dr. Shelley Wright. What I'm showing here is 4 starships. I predict that they would need to travel in minimum size fleets of 4, so that if problems happen on one, they can use the other 3 ships or 2 ships or whatever as lifeboats. Now, these ships don't look for a place to settle. Actually, what they look for is resources, asteroid belts, comets, raw materials. Because if you can harvest those, you can do the one thing that matters. You can replicate the fleet. Let's not forget crews. Old crews have to produce new crews. Fortunately, we're already pretty good at that. And the wave propagates. Okay, here I show a detailed picture of one of our Drake-class starships. This cylinder in the middle is about 4 kilometers long and maybe 1 kilometer in diameter. It rotates at about 1.34 RPM. So at the outer edges of it, it would give the people inside a full artificial G of gravity. It's powered by positron catalyzed fusion drives on each end, about 100 of them. It cruises at 0.2 C. Any faster than that, and you're going to run to too much interstellar matter, and it's going to ablate away all your leading edges. That's going to be a big problem. A typical jump to get to a nearby star would be, and that nearby star would be like 5 to 15 light years away, and that would take 50 to 150 years. You typically have about 1,000 crew members on each ship, but each ship would have a capacity for 4,000. So that way, one ship could theoretically accommodate the crew members of the other 3 ships if something bad should happen. The captains are embedded sentient AI. So you got Captain Frank, Captain Jill, and so on. They answer to a human mission committee. Their mission objective is what they call ISRU, in situ resource utilization among the local asteroids. They do not colonize or terraform local planets. Resource permitting, they attempt to build a new fleet and move on to the next star. As their commercial basis, they search for alien DNA, which they then sequence and share with other spacecraft digitally. And the people on those ships are no longer baseline humans. Interstellar space is not kind to Earthbound biology. Radiation alone makes that clear. So the crew becomes something else, a new species I call Homo galacticus, galacticans for short. These are genetically adapted for radiation tolerance and engineered for multi-century longevity. 500 years is not unreasonable in this context. And with the ability to do genetic repairs as needed, galactican bodies need never experience a use-by date. Century-scale longevity changes everything. You don't need to cycle populations every 80 years or so. You don't need nurseries. You don't need elder care. You reduce the logistical churn that would otherwise dominate a closed system. And you obviate the problem of middle generations being born 5 light years from their destination and wondering what they're supposed to be doing with themselves. Or even worse, the arrival generation finally pulls into orbit wondering what the hell they came here for. It's better for morale if the generation that chose the destination is also the arrival generation. Notice something else. These people don't need planets. They don't attempt to colonize habitable worlds. That's a deliberate choice. Gravity is not universal. A G here, a half G there, 1.5 G somewhere else. Over time, this leads to speciation. You don't get one humanity, you get many, and they drift apart. That's the one thing that the Expanse got right. The physically disparate societies of Earth, Mars, and the main belt do not get along. And even if you did find a truly Earth-like world, the odds are it's already occupied. Microbial life at a minimum, possibly hazardous. Very likely complex life, possibly intelligent. Humanity, especially Western societies, do not have a stellar track record, fun unavoidable, when it comes to encountering new ecosystems or new intelligences. Ask any Native American or African or Australian or Asian. So instead of repeating that mistake on a cosmic scale, just stay on the damn ships. They may visit planets, study them, sample them, extract value. Alien DNA becomes a business within this framework, a new branch of exploration and commerce. Because the most valuable information, or the most valuable resource in the universe at that time is not gold or water, it's information. And biology is information written in DNA. In that environment, genetic diversity becomes a tradable asset, collected, sequenced, digitized, transmitted, and monetized across the network. But they don't stay. They replenish from the asteroid belt, build the next generation of ships and crews, and move on. And over time, the network grows. System by system, hop by hop, replication by replication. That's what a spacefaring society looks like. Okay, if you're interested in the technical side of how this might actually work, I've published it in a series of research papers under the title On Becoming a Spacefaring Society. It's up on Amazon. It lays out the key technologies, the constraints, and the architecture we've been talking about today. If you'd like a copy, I'm happy to send you a free PDF. Or if you want a book, you just got to have the book. You can go to Amazon and search on the Galactican series. Or, like I say, you can just send me an email. I think, let's see. Here we go. My email's right here, efulsing@comcast.net. Please put Mensa in the subject block so that I know who's calling and what it's about. I get so much junk mail, I have a tendency to kind of go through it wholesale and get rid of it. But anyway, send it to me, put Mensa in the subject block, and I will send you a copy of this talk, a PDF of the book I just described, and I recently added a key technology number 8, Israel in the main belt. Okay, if there's one idea I'd like to leave you with, it's this. We don't become a spacefaring society because it's exciting. We become one because eventually it's the only way this story continues. Thank you.
Thank you, Ejner. That was wonderful.